Okay, so chapter 9, this one to me, I think I mentioned this in the chapter 8 Zoom session. I never fully understand why 8 and 9 are separate and why we do part of the part of 8 where I think you kind of, it would help to know 9 before you do 8, but whatever. So I think some things here will start to, like, I kind of think 9 should go first, but we'll see. This, you had an intro if you had intro, but it's basically getting a lot of information from the periodic table. Electron structure, what type of ions will form, how many valence electrons, and then properties like electronegativity, atomic radius, ionization energy, metallic character. And then that's going to segue really well into the next 2 chapters, which are going to look at VSEPR and geometry of molecules. And then that helps us substantially answer questions of intermolecular forces. So the last 4 chapters that we have, to me, go together really well. It's like one big topic. Whereas, like previously, thermo is different from gases, which is different from solutions. Like it's a little bit more disjointed. All of this to me really kind of it all sort of is in sync with one another. So I don't know. I like this section. This is not my favorite section going through it as a student, only because there's not a lot of math, but I think a lot of students would be pretty happy with that. So first thing is the electron configurations. If we go back to the very beginning, we used our periodic table and we use that to help us understand atomic structure for an element. So we could look at boron, for example, and we'd say, okay, well, any atom of boron has 5 protons in the nucleus. Since the mass number is close to 11, we're going to assume that, boron has 6 neutrons in the nucleus. So there's a total of 11 particles. Now we talked about how there's isotopes here. We looked at the weighted averages of isotopes. So again, if we're just using the mass number from the periodic table, we'll go with 11. So 6 neutrons, 5 protons. And then when we talked about, electrons, we just said they're outside the nucleus. And if there are 5 positive particles, there should be 5 negative particles. So what happens now is we get very specific about those electrons and exactly where they are. So what always, what always kind of fascinated about this topic for me, fascinated me about this topic, sorry. My brain and my mouth are not moving at the same speed. What I always found really interesting about this is that, the atomic theory, this was not our first atomic theory that positives are in the center and electrons are outside, right? That doesn't necessarily make sense, right? We kind of think of positive and negative being attractive forces. So the original model was, okay, we'll do a positive and a negative and a positive and a negative, and we'll kind of line them up that way. And that's how it holds everything together. And then, Rutherford came along and blew that out and said, nope, based on my experiment, all the positive is in the center, all the negative is outside the center. And eventually mathematical physicists, genius people came together, and with mathematical probability, kind of with this understanding of, okay, electrons want to be close to the nucleus because positive and negative attract. However, they don't want to be close to each other. So we need to spread the electrons out in some type of, kind of maybe orbit around the nucleus, right? Not exactly sure. So with mathematical probability, they put together the electron structure. And what's amazing is it matches the periodic table like perfectly. A lot of the things that we expect to happen, in fact, do. So I think, everything in your textbook, right, is theory until somebody proves it wrong. But it looks like this atomic theory is pretty good. So first thing is, like we saw with chapter 8, we have our principal quantum number, which is the energy level. And we talked about how that's the first method of organizing those electrons, right? So when we look at a basic atomic structure, we have our nucleus in the center, and then we first organize those electrons into shells, right? And so there's shell 1, shell 2, shell 3, and that matches the row on the periodic table for the most part. Not exactly, but we'll talk about that. Then within so that was N, our principal quantum number. Within that N, we could have our L values, right? And that corresponded to different spatial arrangements. So we remember that when L was 0, what we're going to tie that to now is that was an S spherical subshell. And so it matches the shape of the nucleus in terms of energy. This is the best one for an electron. Makes sense because it matches the shape of the nucleus. So if the electron is trying to orbit the nucleus and it wants to have energetically that the best relaxation it can, it's going to have the same shape as the nucleus. So the S sublevel is lowest in energy within an energy shell. So S is best. Then if you had an L value of equal to 1, these were the P subshells. Technically, there's 3 P orbitals. And in this case, those electrons are limited to only movement along an axis. So you can have electrons that are moving side to side on the x-axis, or up and down on a y-axis, or out and back on a z-axis, or however your brain thinks about it. But basically, the 3 dimensions, we can have electrons moving on any of those 3 dimensions. And so what we saw with our L of 1 is that you can have an M sub L of -1, 0, and +1. And that's because there's 3 different orbitals here. So that's why there's 3 different M sub L values. Then if we had an L of 2, we were looking at a D subshell. And then with our D subshell, instead of being on the axes, those fall in between the axes. So for example, one of them is called a DXY, because now instead of being on the axis directly, it goes between the axes. So if I'm looking over here, this is my XY, then you'd have electrons between that. All right. So anyway, this is matching what we learned in chapter 8, but now we're actually going to put some more information into it with looking at the periodic table. So in terms of our energy level, that is our first type of organization, right? They can organize into these shells, or energy level or energy shell. Within that, there are the subshells or the sublevel, and that's where you can have S, P, D, or F possible. It depends. So what we saw back in chapter 8 was if N is equal to 1, remember your L value maxes out at N minus 1. So if N is equal to 1, then L has to be equal to 0. And that's it. That's the only possible L value when you have an N of 1. So this is a 1s space. It's in the first energy shell, right? The shell right closest to the nucleus, and it's a spherical orbit. When your N is equal to 2, you're now in the second shell. You can have an L value of 0 or 1, which means that there is a 2s or there's a 2p. They're both in the second shell. When your N is equal to 3, your L can be 0, 1, or 2, which means that there's a 3s, a 3p, and a 3d. And then N is equal to 4 means you can have L of 0, 1, 2, and 3. And so that means there's a 4s, a 4p, a 4d, and a 4f. Now, if we go and we match that onto the periodic table, the S, P, D, and F are all very specific regions on the periodic table. So it's always amazing how this quantum theory matches our periodic table, right? Like the structure, the organization of it, it's all pretty amazing to me. So over here on the left side, when we look at our alkali metals and our alkaline earth metals and hydrogen, and technically just for the purposes of electron configurations, I would put helium over here as well. We'll talk about that. This corresponds to the S subshell, right? And again, that's when your L value is equal to 0, bringing in what we learned in chapter 8 into chapter 9, right? So that's our S space. And again, like we talked about, that is our spherical shape. So here's my nucleus in the center. Here's my S subshell. That is, in terms of energy, of all the subshells we have, S, P, D, and F, S is the favorite, right? Because again, it matches the shape of the nucleus that is energetically best. When we go to the middle, right, if we start here at scandium, yttrium, right, and we go over to zinc, cadmium, right, this block right here, which we of course learned was the transition metals, this corresponds to a D sublevel when your L value is equal to 2. All right, so I'm going to write that up. L value here is equal to 2. Which means that your M sub L values could be -2, -1, 0, 1, and 2. Now we don't need to worry about those because that was chapter 8, but the reason why I'm doing it is because it's going to segue nicely when we start doing orbital diagrams. All right, so just kind of reminding us of what we had. Up here with S, L is equal to 0, which means M sub L is only equal to 0. All right, so we have S for our alkaline earth metals, hydrogen and helium. Then our D, right, that's for our transition metals. So scandium on down, over to zinc, and then on down. So there's my transition metals. Then if I slide over here to the right, the 6 tall columns that we have on the right, this is our P sublevel. And this is when you have an L value of equal to 1. So your M sub L value could be -1, 0, or +1. And what we talked about here was this is when those electrons are on the axis, our axes, right? So they're on the X, Y, and Z. There's 3 different axes because there's 3 different M sub L values. So it matches very nicely. So we have S, P, D, and then down at the very bottom, let me zoom out here for just a second and I'll zoom back in. When we get down to the very bottom here with our lanthanide and actinide series, this is our last subshell, at least until they keep building on more elements and maybe we go past this, but we're at the moment, we're maxing out at the F when you have an L value of equal to 3. All right, so those are our 4 subshells. So within an energy level, right, energy level 1, what we talked about when N is 1, the only possible value for L is 0. So that's why hydrogen and helium are in the first row and there's nothing after that. When you go to the second row, now you have an N of 2, which means L could be 0 or it could be L of 1. So that's why you see there's only a 1s, but in the second row, there's a 2s and a 2p. When we get to the third energy level, we can have, since N is 3, we can have an L of 0, 1, or 2. So here's my 3s, here's my 3p. Then the question is, well, where's 3d? Well, 3D turns out to be here in the 4th row. So this is a glitch that we have on the periodic table. So I guess it's maybe not so perfect, but in my mind, it looks like it's pretty perfect. There's a little glitch that we have to remember here. The reason for that is going back to what we talked about, S, the spatial arrangement of that is energetically favorable, like by a lot compared to the Ds. So what happens is it actually turns out when the electron is filling the atomic structure, right? We're putting electrons into this atomic structure, that the electron actually prefers to sit in the 4s rather than the 3d. So when we get to the D block, the transition block, you want to actually take your rho -1. So if we're doing our filling, we'd fill our 1s first, then we'd fill 2s and 2p. Then we'd fill 3s and 3p. Then we'd have our 4s. And then right here, scandium, row number 4, but 4 - 1, scandium means that this starts our 3d, right? So little glitch there. So 3d from scandium to zinc. And then back to normal, gallium starts the 4p. So the next shell, right, rubidium starts it. We've got our 5s. Same idea, yttrium here would be the 4D instead of 5, because even though it's row 5, it's a 4D. And that would take us to cadmium. And then indium, back to normal, this is our 5P. Right, and then we'd have our 6S for cesium and barium. And then what happens here is we've got our second glitch. When I look at barium, it's atomic number 56. When I look at lutetium, it's 71. So where are those elements, right? From 56 to 71, those are all down here. The lanthanum, lanthanide series, this starts 57 right here. And so remember how we said that when you had an N of 4, you can have an L of 0, an L of 1, an L of 2, or an L of 3 with the F. So the lanthanum, the lanthanide series, that gap in atomic number between barium and lutetium, right? This right here, and I'm going to put like a little star, is right here where these elements are coming in, the lanthanide series. And for F, kind of like D, we have a little glitch we have to remember. We have to take rho -1. So we're in row 6. So cesium and barium, this is our 6s, right? So there's my 6s. Then when I go to this gap, I'm going to go down here. I'm in row 6, but the lanthanum, and why did I say rho -1? I'm sorry, rho -2. So this is 6s, and take away 2, 6 - 2, lanthanum starts the 4f. All right, and the 4f would be filled. And then we go to lutetium, and this is the 6th row, but lutetium, this would start now the 5d. And then we'd finish out the 5d, and then we continue with normal counting. This would be our 6p. So what we're going to be looking at is we're going to look at what are called electron configurations, which in my mind, the way I think about that is we're just giving an address to all the electrons for the whatever atomic structure we're looking at. And so like if it's something like hydrogen, it's really easy, right? Hydrogen only has 1 electron. So we just have to give the address of that 1 electron. and we say, okay, it's in the first energy shell, it's in an S subshell, and there's only one electron in it. So we say it's 1s1. Helium would be 1s2, atomic number 2 electrons instead of just one. All right, so that's what we're going to be looking at here first. So the periodic table, I'm going to keep coming back to this. There's something similar that's been scanned and placed in the folder. I'll double check, but if not, I'll put mine in there, but it should be in there. All right, okay, so energy, right? S, P, D, and F goes in that order. S is energetically best, then P, then D, then F. The 1s is the best seat in the house. It's in the first energy level. And we talked about that when we were doing chapter 8, that the closer the electron can get to the nucleus, the more stabilizing that is, because of those opposite attraction forces, right? Electrostatic forces are very stabilizing. So the 1s place is the best place to be, right? So if we're going to take an electron away from the 1s and bump it up to a higher energy level, we have to put energy into that. We saw that that would be endothermic. But if the electron can relax back down to 1s, then it's exothermic, because again, getting closer to the nucleus is better. All right, so this matches what we learned in chapter 8. So 1s is always best. Then we go 2s and 2p and 3s. Now, when I was learning this, I remember very well, my professor came up on the board and he said, okay, in the first energy level, you only have an S sublevel, right? Because if your N is equal to 1, your L can only be equal to 0. When you get to the second energy shell, you can have a 2s or a 2p, then 3s and 3p and 3d, and then 4s and 4p, 4d and 4f, and then 5s and 5p and 5d and 5f, etc. And so don't worry about this, but and again, I don't think this is the easiest way to do this. I just remember this is how I learned it. He said, okay, what you do is you fill the 1s first, then you fill the 2s, then you would do the 2p and the 3s, then the 3p to the 4s, then you do the 3d, 4p, 5s. And so I remember when I was learning this, drawing these arrows, being like, okay, this is the order of filling. We fill the 1s, then the 2s, then the 2p, then the 3s. But I find it so much easier to just look at your table and follow the table, right? We fill the 1s first. We go in the order of the atomic number, then the 2s, then we come over here. This is still row 2. This is now the 2p because we're in the p block. Then we have our 3s, then the 3p, then 4s, and then the 3d, right? So I think it's much easier just to remember that when you get to the D block, take row -1, rather than drawing the arrows and lining all that up. But that's just my personal opinion. Okay, so what we're going to do again is look at the electrons outside the nucleus. Exactly where are they? Right, so when we were talking about hydrogen first, right, the simplest, hydrogen, easy electron configuration, it's 1s1, right? So the 1 here is our N, like we learned back in chapter 8, last chapter, right? That's the energy level. Then the S, right, there's our subshell or the block on the periodic table. And then the superscript up top is the number of electrons inside, right? So that is our first and easiest electron configuration. Hydrogen has a 1s1 configuration. So then what we have to talk about is, okay, we've talked about the energy level, the sublevel. Within the sublevel, there are specific orbitals. And the rule is that only 2 electrons can occupy any one orbital space. All right, so that is a rule with electron configuration. So there's this one specific orbital space, and for some reason in my mind I thought of it like seats on a bus, like a school bus. So only 2 kids per bench seat, and so I thought like the orbital, okay, only 2 electrons per box, per orbital space. So when you look at this, how does the block on the periodic table match to the orbital itself? And this is going to go back to what we learned with quantum numbers. So in an S sublevel, there's only room for 2 electrons. And we know that because there's only 2 columns here, because every time we add an electron or add an atomic number, we're adding an electron. So we have room for only 2 electrons. So in the S sublevel, we have a max of 2 electrons. And so what that means, if 2 electrons can fit in any one orbital, that means there's only 1 orbital. All right, and that is that spherical shape. All right, so focus. So that's the spherical shape. So that shape that mimics the nucleus, right? That is that orbital, right? That's the orbital around the nucleus. So the only thing that's different from a 1s to a 2s to a 3s is just the distance from the nucleus. So like the 1s, then the 2s, then the 3s. They all look the same. They're all a spherical shape. It's just the radius of it. How big is it? So in that one spherical shape, you have a max of 2 electrons, right? 1, 2, 2 electrons. And so going back to what we learned in chapter 8, if L is equal to 0, which means we have an S subshell, that means that our M sub L is 0, which means there's only one orbital, right? And that's what that is right there, the one orbital space. If I go over to P and look at the P block real quick, if I have room for 1, 2, 3, 4, 5, 6, right? I have a max of 6 electrons here. That must mean divide by 2, there are 3 different orbitals, right? 6 divided by 2, I can fit 2 electrons in each orbital. So 2 times 3 is 6. That's why I've got room for 6. And that matches what we had in chapter 8. If L is equal 1, that means we have a P sublevel. Then M sub L values could be -1, 0, or 1. There's 3 possible values because there's 3 possible orbitals. And that is the x-axis, the y-axis, and the z-axis. So if I'm just looking at one orbital, like the px orbital, I can only fit 2 electrons. If I'm looking at the p sublevel, all of that combined, I can fit 2, 4, 6. All right, so the 6 electrons is always for the sublevel, right? Like the max of 6 sublevel. But the rule with an orbital is an orbital can only hold 2. Now, if I look at D in the middle, the transition metals, right? If I count over, I've got 1, 2, oops, it froze again. So scandium is the first spot, titanium the second. If I count over 3, 4, 5, 6, 7, 8, 9, and 10. For the whole sublevel, I have a max of 10 electrons, which means that there must be 5 different orbitals. And if I look, that matches what we learned, right? If L is equal to 2, M sub L has 5 different values because there's 5 different orbitals. All right, and then down at the bottom with F, you'll see if you count over, there's room for 14 electrons. And so what that means is that there are 7 different orbitals. And the M sub L values there would be -3, -2, -1, 0, 1, 2, and 3. So there's 7 different values there. Okay, so that's how it matches what we did in chapter 8. So when we do those electron configurations, we're going to basically read like a book. We go left to right across the periodic table, and we're going to, again, put an address for all the electrons that are in whatever atomic structure we're looking at. So if I go to the next page on the notes, the next thing in the next paragraph, right, we had hydrogen 1s1, helium 1s2. If we look at lithium, right, we're going to stop here. So we always start 1s because that, again, that's where the first electrons always go, closest to the nucleus. 1s fills at 2. Lithium is now 2s1, first spot. So we know that lithium has 3 electrons, 1s2, 2s1. So there's my 3 electrons. So when I look at those, the superscripts, right, the number of electrons, 2 plus 1, that's my atomic number for lithium. That's 3. All right. So electron configurations, that's the first thing that we're going to do. So I'm going to just do one. It's not specifically in here, but up here in the margin. Let's say we're going to do phosphorus. All right. So phosphorus is atomic number 15. So we know there's 15 electrons here. Remember, the first electrons always go here, 1s, right? And the 1s we know maxes out at 2. All right, but the periodic table tells us anyway. We know 1s, right? 1s fills at 2. Then the next place we would go is 2s fills at 2. And then going with our atomic number, now we have to come over here to boron, which is the 2p, and it fills with 6. All right, so let me write that down. We've got 2s2 and then 2p6. All right, we keep going until we hit phosphorus, right? So we're not there yet. After the neon, 2p6, we go to 3s2, sodium, magnesium, that's the 3s2 spot. And then to get to phosphorus, we would have our 3p, 1, 2, 3, so 3p3. So to finish this out, we'd have 3s2, 3p3. So when I look at this, there should be 15 electrons here, 2, 4, 10, 12, 15. So there's my 15 electrons. Again, the way I always thought about it was I'm assigning an address to all those 15 electrons, right? The first two are in the first energy level in a spherical orbit. The second two are in the second shell, a little bit farther away from the nucleus, but same spherical orbit. The next 6 are going to be along those axes, X, Y, and Z in the second shell, right? So that's what we're doing with these electron configurations. And what it's going to help us understand is first what type of ions to expect. Like we learned in the beginning, phosphorus should be -3, but why, right? So we'll look at that. And then when we go into covalent bonding, where instead of looking at ions, we're looking at electron sharing, we'll understand why phosphorus really likes to take 3 bonds typically, right? So those are the kinds of things that this will help us look at. All right, now the other thing that we're going to talk about is what is the difference between a valence electron and a core electron? When we talk about ion formation or electrons that are being shared in covalent bonding, it's always the valence electrons that engage, right? So when you think about your atomic structure, you've got your nucleus, first shell, second shell, and now the third shell, right? So if we're looking at phosphorus, the outermost electrons are in that third shell, right? So these right here, the 3s2, 3p3, those are the valence electrons. In other words, valence means the electrons in the highest occupied shell. So imagine if phosphorus is going to engage in bonding, it's not going to use the electrons in the first shell or the second shell because those are called core electrons. There are electrons past that, right? So the 1s2, 2s2, 2p6, that's all core electrons. They don't react. Imagine if you're trying to do any kind of electron sharing or electron transfer, you're not going to do that with the 1s2 electrons here for phosphorus. You're going to do that with those 3s2, 3p3 electrons. Right, so that'll be another big thing that we have to focus on is the core versus the valence. The valence are the most important because again, they decide what happens with the bonding. So we'll spend a lot of time talking about valence. All right.
Really quick question.
Yeah.
The valence electron is always the last S and P, right?
I would love to say always, but as with everything in chemistry, there's no always. The transition metals make it problematic. So in intro chem, we basically stuck with what are called the representative elements, right? So we were really just looking at the S electrons and the P electrons. And in that case, yes, whatever is in the outermost S and P, those are your valence. What happens with transition metals, and we'll talk about this when we get there, because even though this is row 4, this is a 3D, if the D shell is not full, those also act as valence. So, but we'll talk about that because that's something new that we didn't do in intro. So I would love to say it's always S and P, but it's not. It depends. If it's a transition metal, it might be the D as well. All right, so
Okay, thank you.
Yeah, you're welcome. We'll come back to that. All right, so rules with the electron configurations, they always occupy the lowest energy orbital first, right? The 1s always fills first. Best seat in the house. No more than 2 electrons can fit an orbital. All right, we'll look at that more when we do orbital diagrams. If you have 2 electrons in the same orbital space, like remember on the p-axis, like just px, then those 2 electrons will have opposite spins. All right, and you remember back in chapter 8, we had an m sub s of positive or negative 1/2. That's what that's referring to, that it's the magnetic spin quantum number, that they have opposite spins. The idea is that if I've got 2 negative particles right next to each other, repelling each other, if I have them spin in opposite directions, it's going to offset that repulsion just a little bit and make it a little bit energetically, just a little bit better. So anyway, that's why you have plus and minus 1/2, but we'll get there. And then with occupying their own orbital, we'll see that when we do orbital diagrams, but we're not quite there yet. All right, valence versus core, like I just mentioned, we're going to look at that some more. So this is kind of all the background information that we're going to need, but now we're going to start doing some examples. All right, and we're going to talk about all those pieces that we had. Okay, so the electron configuration, SPDF notation, that is just to be kind of, some books make the distinction between an abbreviated configuration, and I'm going to show you both of those. So the SPDF, like the complete notation. So basically, first thing is, look at selenium on your periodic table, all right, and we know it is number 34. So for selenium, I know I have 34 electrons to assign an address for, right? The first ones, right, always go 1s2. Every electron configuration starts at 1s2 except hydrogen, which is 1s1. Then going with the periodic table, right, 1s2, 2s fills at 2. Then we'll come over, do 2p6, and then we'll have our 3s2 and our 3p6. So I'm going to kind of pause there for a second. So 2s2, 2p6, 3s2, 3p6. Right, so if I gave you that configuration and I said, what element was that, right? 1s2, 2s2, 2p6, 3s2, 3p6, what I could do here is a couple things. 2, 4, 10, 12, 18. It would be atomic number 18, which would mean it's argon. Or that last thing that you write, the 3p6. Here's row 3, p block 1, 2, 3, 4, 5, 6, argon, right? But we're not done. We have to keep going to selenium. So this was our next glitch. After argon, we go to potassium, which is our 4s, fills at 2. Remember, when you get to the D, even though this is row 4, this is a 3D, and it fills at 10. And then to finish out, to get to selenium, 4p, 1, 2, 3, and 4. So to finish out, 4s2, 3d10, and 4p4. Now I can double check my work. All of those superscripts added together should be 34 because that's the atomic number. 2, 4, 10, 12, 18, 20, 30, 34. Now, not to be confusing, I get it, but I never like that books do this, the textbooks. What they're going to do a lot of times is they're going to put the order with the principal quantum number. So rather than going with the order of filling, which is what we just did, because that's how the atomic structure is filled, it goes in that order, just like reading the periodic table left to right. The book will say, you know what, let's order all of the electron configurations by the principal quantum number. So in other words, we'll do quantum number 1 first, 1s2, then quantum number 2 first, 2s2, 2p6, then quantum number 3 first, 3s2, 3p6, and 3d10. So it basically moves that over to go 3, 3, and 3. And then to finish it, 4s2, whoops, that was not a good 4, and a 4p4. So the book just reverses the order of the 3d10 and the 4s2, putting all of the quantum number 3s together, and then all of the quantum number 4s together. The advantage to that I could see as being, might be easier to identify the valence, like we talked about. The highest occupied shell here is the 4th shell. So the 4s2 and the 4p4, those are the valence electrons. All right, everything else prior to that is core. So that maybe is one advantage. But I always go with the order of filling. On the quizzes or tests, you pick which you prefer. But I always thought it made more sense to just go with the periodic table and do the order of filling. So we have all 34 electrons here. And what we talked about was the valence electrons are the ones that really do all the work, right? So what we're now going to look at is, okay, what is the noble gas core abbreviation? And then do an electron configuration doing a noble gas core. So instead of starting at 1s2 and working all the way through, imagine like doing lead, right? That would be a pain. What you can do is for any element, find the noble gas core. So selenium, right here on the periodic table, your noble gas core you find by going up one row and all the way to the end, right? Noble gases are all the way at the end. So selenium has an argon core. If we were looking at tellurium, it'd be a krypton core. Let's see, a question came in. If it's organized by quantum number, will the valence electrons usually be the last 2 sublevels? So again, I would love to say yes, but not necessarily, because the transition metals, if you're looking at a transition metal, which I'll do next, the transition metals get a little weird because you would do, if you switched it where you did the 3D first and the 4s second, then it might look like the 4s was only the valence, but it's not. The 3D would be as well. So if it is a representative element where it's in the P block or in the S block, the answer to that question in the chat box would be yes. That if you do the order of quantum number, as long as the D is filled, whatever's in that highest occupied shell is your valence. All right, now if we do the noble gas core abbreviated configuration, rather than starting at 1s2, we would start, like we said, for selenium, it would be at the argon core. And so that'll save us a little bit of work. So instead of starting 1s2, 2s2 going all the way through, we pick up from argon. So after argon, we have our 4s2, our 3d10, and our 4p4. So we saved a little bit of writing. And again, if you were looking at the book answer would be, okay, argon, we'll do the 3d first, and then we'll have the 4s2 and the 4p4. All right, so the noble gas core just helps us not have to write 1s2, 2s2, 2p6, 3s2, 3p6. We took all of that and we put it in the argon core. All right, now the either way, this electron configuration, the first one we did, right, SPDF notation, that's the complete configuration. So we wrote all of those 34 electrons out, right? So all of them are there. If we do the noble gas core abbreviated, try to see if I can get it to focus. There we go. Then we save ourselves some time. And again, when you go to your periodic table, whatever element you're looking for, if it's 10, it's a krypton core. If it's oxygen, it's a helium core. Sulfur has a neon core. Your noble gas core is always up one row and all the way at the end. So the orbital diagram, though, this is where we're going to look at that magnetic spin quantum number, how they have opposite spins. All right, so what I'm going to do for the orbital diagram is I'm just going to focus on the valence electrons, because that's kind of, well, let me do those first. So if we have a 4s2 and a 4p4, what I want to do here is go back to what we were thinking about the M sub L value. If we're looking at an S, right, that means our L is equal to 0, which means M sub L is equal to 0, which means there's only one orbital. If we're looking at a P, right, where L is equal to 1, that means M sub L could be -1, 0, or +1. There are 3 different orbitals. So when we do an orbital diagram, you can either use a dash to represent an orbital, or you can use a box. I've seen both. So when you're doing an orbital diagram, if you're doing an S subshell, there will only be one box, right? Because the M sub L value is only 0. If you have P, you're going to do 3 boxes, because M sub L could be -1, 0, or +1. If it's D, you're going to have 5 boxes, values M sub L -2, -1, 0, 1, and 2. And if you had to do F, there'd be 7 boxes, -3, -2, -1, 0, 1, 2, 3. Now, when we do the order of filling, the instructions were, if number 1, no if, just number 1, no more than 2 electrons can fit 1 orbital space. So in each one of these boxes, there's only room for 2 electrons. That's it, no more than 2. If you're going to put 2 electrons into the same orbitals, we give them our same orbital. We give them opposite spins. So that's where the M sub S is +1/2, -1/2. So we'll show that with an arrow up versus an arrow down to show that they would have opposite spins. The last thing on there was, and this was on the previous page, that electrons really like to sit in their own seat if they can. So here's how you fill your orbital space. The 4s2, we don't have any options there. We've got one space, max of 2 electrons. In this case, there are 2 electrons in it. So we're going to show arrow up and arrow down, right? Opposite spins, because again, that's one of the principles that offsets the repulsion, the magnetic spin quantum number, +1/2, -1/2. So they have opposite spins. So the arrow here is representing an electron. When I go to fill the 4p4, however, do I want to put 2 and 2, or do I want to go 1, 1, 1, and then a 2, right? So 2 in the first box, 1 and 1. And the idea is that these 3 orbital spaces, because they're in the same subshell, same 4p, they are degenerate, which means they are equal in energy. So the first electron comes in, and you really couldn't tell me for sure where that electron's going to go. I mean, the electron doesn't care if it's on the x-axis, y-axis, or z-axis, right? It doesn't matter. So who knows exactly where it goes. But whoever made the rules said the first electron comes into the first box and it has arrow up. Again, you can't prove that part, but this is just the rules of orbital diagrams. The second electron that comes in says, okay, I can pair with the first electron here and lose some of my stabilizing energy because I'm now repelling against this negative particle, or I can sit in my own seat and not have to lose some of that energy because I'm being repelled by something I don't like, right? So the second electron comes in and it goes to the second space and again, arrow up, right? The third electron, same idea, goes now into the third box, arrow up. And now the fourth electron for the selenium doesn't have a choice. It has to now pair, and that's okay. One of them, right, will have to be a pair. The other two will be singles. And again, you couldn't tell me that it's the PX or the PY or the PZ, but the order, like the rules of orbital diagrams say, when you do your order of filling, you start left box, arrow up, and then up, and then up. And then now that you have to pair, you go back to that left box and you pair down. So when I look at selenium, the valence electrons, the 4s2, those are paired. And then the 4p4, I have a pair and two singles, right? And so what we know about selenium being in the oxygen family, it likes to have a -2 charge, meaning it likes to pick up 2 electrons, which kind of, is counterintuitive because I just got finished saying, but electrons don't want to like pair, they repel against each other. So why does it want 2 electrons? And it's because there's something that happens when we get to that noble gas S2P6 configuration where a stability switch clicks on. So something special happens here. So selenium really wants to look like krypton. So even though electrons don't like pairing with each other, if it can pair and get to that P6, it's extremely stabilizing, right? So that'll come up more later. All right, so the next thing is with the examples, I've got different orbital diagrams, so just going through the rules we just talked about. Okay, so first thing is let's identify what element this is, and then we'll talk about whether or not it's correct or not. I have the arrows represent electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so there's 14 electrons here that are shown. So if I go to my periodic table and I look at atomic number 14, this should be silicon, right? So this should be a configuration for silicon. Now let's talk about whether or not it's a good configuration. Everything starts out looking pretty good, right? 1 box for the S, we talked about that, 2 arrows, opposite spins. 1 box for the 2s, same thing, opposite spins, arrow up, arrow down. Then the 2p, there's 3 boxes here or dashes, right? 2, 4, 6, 3 spaces, right? Up, down, up, down, up, down. So that looks good. The 3s2, 1 space, 2 electrons in it, opposite spins, that looks good. But then when we get to the 3p, like we just talked about, rather than pairing, what this would prefer to do is have arrow up and arrow up, right? So those 2 electrons in the 3p will sit separately because they don't have to lose some of that energy because of repulsion. Now the next one, I've got 2, 4, 6, 7, 8 electrons. So if I look at 8 electrons on the periodic table, that should be oxygen. So this should be the orbital diagram for oxygen. 1s2 looks good, right? 2 arrows, opposite spins. 2s2 looks good. 2 arrows, opposite spins. And then the 2p4, up, 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 and then we pair down at that first left box. So this one is a good, valid orbital diagram. So this one looks good. Then if I look at the next one, just to kind of reinforce a point, this also looks like, it's 8 electrons, it's also oxygen. But what we changed here was instead of going arrow up on the last 2 orbitals, we have it as arrow down. I know that's not really easy to see with my camera, but these are both arrow down. And so again, I don't know how you argue which way the electron is spinning in the 2px space or the 2py space, whatever. But again, whoever made the rules, they said we always are going to start by going arrow up and then we pair down. So this right here is not valid because those 2 electrons right here at the end, those should be arrow up, right? So that won't work. All right, so I'm gonna kind of use the back of the page here really quick and do another example of an electron configuration abbreviated with the noble gas core. Look at valence electrons, look at an orbital diagram, and I want to do a transition metal because they get a little bit tricky. And we'll look at these more when we do diamagnetic and paramagnetic. All right, so let's look at vanadium. All right, so vanadium, element V on the periodic table, it's atomic number 23. All right, so I am looking at vanadium right here, number 23. So if I'm going to do the complete configuration first, we're going to start 1s2, and then 2s2, 2p6, and then 3s2, 3p6, and then we'd get to 4s2, and then we go for our glitch, right? It's 3D, and for vanadium, 1, 2, and 3. Oops, sorry, 1, 2, 3. All right, so if I add up all my superscripts, right, 2, 4, 10, 12, 18, 20, 23, there's my 23 electrons. Again, if you were going to look at the book answer, it would have 1s2, then 2s2, 2p6, then 3s2, 3p6, 3d, 3, and then 4s2. All right, and that's where I was like, I don't like this scenario. So question that came up earlier was, if we do the book way, if we organize it by the principal quantum number, is the last thing that we write down the valence. So the transition metals are what make the whole question about valence electrons maybe a little bit tougher, because normally the rule is a valence electron are the electrons in the highest occupied shell. Well, for vanadium, the fourth shell is the highest occupied shell, right? So we know that this is valence. But with transition metals, any unfilled D is also valence. Now unfilled. So because the 3D for vanadium is not filled with 10, it only has 3, this is also valence. So all of that right there, these are your valence electrons. So transition metals, I'm going to write this out. Transition metals, the valence electrons are the highest occupied S electrons, right? The 4s that we saw, and any unfilled D electrons. All right. So what happens with the electrons, the 4s, like we talked about, those fill before the 3d3. And when that filling happens, the 4s, right, is lower in energy to start than the 3d. So the electron comes in and says, oh, I like the 4s better, so I'm going to go there, and then I'll start going into the 3d. And then as the d orbitals begin to fill, they actually lower in energy. And then what can happen is, if the d gets completely filled, it drops below energy than the 4s. So it's a little screwy. Like, we don't have to really worry about it too much. Just remember that if you're looking at a transition metal, normally valence, highest occupied shell, that's what we did in intro. But now any unfilled D also acts as a valence electron. And I think what you want to kind of make sense of that is the valence electrons are the ones that do the bonding, right? And we understand that once a subshell gets filled, there's some kind of stabilizing effect from that. So if the 3D isn't filled, right, that's not stable. So those are going to be reactive, as well as the 4s2. So we take the outermost electrons, in this case, the 4s2, and any unfilled D. So in this case, the 3d3. So the transition metals, valence electrons. So if we're looking at vanadium, the valence electrons, just to kind of make sure I'm clear about this, is the 4s2 and the 3d3. All of those are valence. All right, then if we were going to do the abbreviated configuration for vanadium, where we do the noble gas core, just practicing that one more time. The abbreviated configuration is always finding the noble gas core. So here's vanadium in row 4. I go up to row 3. It has an argon core. And with that noble gas, you put it in brackets. And then past that, we would have the 4s2, 3d3. Right, so same configuration, right, as what we did up here. We just are using an abbreviation with the noble gas of argon. All right. Then if we were going to do an orbital diagram. So let's do that. All right. So for the orbital diagram, I don't know why I put an E on that. If we have an argon core, we don't have to worry about that. Let's look at the 4s. All right. Because it's an S, we're going to have one box. And we're going to have two arrows, opposite spin, one up, one down. When I go to make the 3D, a lot of times what will happen here is students will say, well, I only have 3 electrons, so I only need 3 boxes. But you have to draw all of the possible orbitals that you have for the sublevel. And so what you want to remember is that the D has room for 10 electrons, which means there's 5 different orbital spaces, right? Matching that quantum number, the M sub L. 5 different values. So even though we don't have that many electrons for vanadium, we still need to draw 5 boxes. All right, and then this is our 3D space. So first electron comes in, left box, arrow up. Second electron, second box, arrow up. Third electron, third box, arrow up. So that would be the orbital diagram for the vanadium. All right, 4s2, 3d3. All right. So we've gone through electron configurations, orbital diagram, valence versus core. And I think now what we want to talk about is kind of a little bit more repeat, and then we'll look at ions, because this is all going to change when we look at ions. All right, so if I go back to where we were in the notes, we had just looked at possible orbital diagrams, and then right underneath that, there's a section called representative elements. So the representative elements, this is what we covered in intro, right? Representative are the S and P elements. So looking at the periodic table, any of the elements that are in the S block, the alkaline earth metals, or the P block, right? Boron, carbon, nitrogen over there. And for this, it's very simple because there's no D orbitals that we have to worry about. The valence electrons are just those S and P. So this goes back to Adam's question. This is where S and P are it. Those are all the valence electrons. So if I'm looking at an alkali metal or hydrogen, they all have the same valence configuration. They're all S1. So if I go down my alkali metal family, lithium, sodium, potassium, right? They all have an S1. The N changes, right? Lithium is 2s, sodium is 3s, but they're all the S1 configuration. The alkaline earth metals, group 2, same thing. It's just S2 instead of S1. The only thing that changes is the shell that it's in. Beryllium is 2s2, magnesium is 3s2 for the valence. When we go over to number 3, the boron family, so boron, aluminum, gallium, indium, thallium, they all are at S2p1. The carbon family, S2p2. Nitrogen family, S2p3. Oxygen, like we saw up above, was the S2p4, and then the halogens, S2p5. All right, so the number of valence electrons, what you'll notice, is the group number on the periodic table. This is going to be really important when we do Lewis structures in the next chapter. So number of valence electrons here. If it is a group 1 alkali metal, there's 1 valence electron. Group 2 alkaline earth metal, 2, right? The boron family, 3 valence electrons. Remember how we saw aluminum is always a +3 charge? That's why, right? 3 electrons to get rid of. The carbon family has 4 valence electrons. Nitrogen is 5. Oxygen family has 6, and the halogens are all 7. Right, so that's our number of valence electrons, right? The electrons in the highest occupied shell. So again, whether it's a 2s1 or a 3s1, there's still just 1 valence electron, whether it's lithium or sodium, right? And then of course, the noble gases at the end, they have 8. They have what's called the octet rule, S2p6, right? So the transition elements, like I was talking about with vanadium, now your valence electrons, and I wrote this out, this is what's new. We didn't talk about this in intro, are the highest N, right? The valence electrons are the highest occupied shell, and any unfilled D. So like we saw with vanadium, we had the 4s2 and the 3d3. Those were all the valence electrons. Now let's talk about zinc. Okay, so if we look at zinc, zinc has an argon core, and then it has 4s2 and 3d10. All right, so now what, right? it says the highest N, so there's my 4s2, and any unfilled D. But this one, the D is filled. So for zinc, the valence electrons here is only the 4s2. And remember what we learned, zinc is always a +2 charge. That's why, because those are the only valence electrons for zinc. Once the D orbitals are full, they're stable and they act like core electrons. But if the D isn't filled, then they're not stable and they act as valence. All right, so that's sort of the peculiar thing with transition metals. The other thing that's peculiar about transition metals is that we have some exceptions. And we didn't have this with the S&P elements either, but this happens when you're in a D4 column or a D9. So when I look at my periodic table, 1, 2, 3, and 4, here's my D4 column, my chromium, and then my D9, my copper, right? What happens here, let's look at chromium. All right, chromium, we think, if we go with the order of filling, it should be 4s2, 3d4. And so if I think about that orbital diagram, I'd have my 4s with 2 electrons in it, and then my 5 different boxes for the D, and it would be up, 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 and up, but it has an empty box at the end. So what happens is, it all comes down to energy, right? The 2 electrons in the 4s, they lose energy because they have to share and they're repelling against each other and they don't like that, right? So they lose some energy because they have to pair. So what'll happen here is the energy lost by pairing is not as bad as the energy lost by moving one of these over into the 3d4, right? In terms of energy, when I look at an energy diagram, your 4s is here, 2, 3, 4, 5, and your 3d is here. Sorry, that ran off, but here's your 3d, here's your 4s. So the electron pair that are in the 4s, right? Because they're paired, they lose some of their energy because again, they're repelling against each other. It turns out that repulsion causes them to lose more energy than if they just lose the energy by moving up. So that 1 electron here moves up and it becomes, instead of a 4s2 3d4, it becomes a 4s1 3d5, right? So energetically, that's actually better. And as I mentioned with those D orbitals, as they start to fill, they drop in energy. And so the amount of energy lost by repulsion is more than the energy lost by just moving up to that D space. So that happens with chromium, molybdenum, tungsten, right? Everything in that column for the D4 slot. All right, so that exception, right? The chromium, molybdenum, tungsten happens all the way through. Then the same thing happens when you have the D9 spot, right? So if I look at silver, okay, silver has a krypton core and then a 4s2, sorry, a 5s2 and a 4d9. So the 5s, right, paired 1, 2, 3, 4, 5, and then you have 2, 2, 2, 2, and then a single. All right, and so here you might say, well, that doesn't help because they're paired in the S, and then if I move it over here, they're going to be paired in the D. But remember, the D orbitals are kind of weird. When they start to fill, they drop in energy, and actually once the D orbitals are full, they actually switch in energy in order. They drop to be below the energy of the 4s. So it's energetically better to take that S2, that electron in the 5s, and move it over into that last space on the D. So for silver, it's a 5s1 4d10. And that's why silver is always a +1 charge, because now that filled D is no longer valence. It's only the 5s1 that's valence, like we talked about with zinc. Now with copper is a little bit different. The energy values are not set in stone here. So the copper, what happens with the 3D and the 4s is they're much closer in energy. So it actually goes back and forth. Like sometimes it's going to be a 4s2 3d9. Sometimes it's a 4s1 3d10. And we know that because the charge on copper can be a +1 or a +2. So that's why we know that the exception is not absolute with copper. But the book likes to teach it like it is. So we'll go with it. All right, so these are some of the exceptions just to remember. The chromium, right? Same with molybdenum, tungsten. Instead of an S2D4, it becomes an S1D5. And then that 9 slot, the copper, silver, gold, instead of an S2D9, it's going to become an S1D10. All right, so molybdenum, just to kind of reinforce one of the exceptions, it's number 42 on your periodic table. And we're going to do noble gas core abbreviated, so we can save some writing here. So for molybdenum, noble gas core, we go up all the way to the end. It's got a krypton core. And then to finish it, right, what we expect would be a 5s2 and a 4d 1, 2, 3, 4. Right, so if we just do the order of filling with the periodic table, that's what we would expect. But that's not what we get, right? We would have the krypton core. And then one of those electrons that is paired in the S space says, you know what, I'd rather sit by myself if I can. And it does that, it moves over and occupies that empty box or the empty orbital for that 4D. So one of the exceptions becomes a 5s1 4d5. All right, now for bismuth. Bismuth looks like it's going to be a bad one because it's a atomic number 83. We're going to do the orbital, the noble gas configuration, so that'll save us a little bit. So for bismuth, though, our noble gas core is xenon, right? So xenon only has 54 electrons in that structure, and I have to get to 83. So where are the rest of those 29 electrons, right? There's a lot. Where are they? So if we do the order of filling, after xenon, we have our 6s2, cesium and barium. Okay, so let me write that first. So we have the xenon, then we have 6s2. Then what we want to remember is we get that gap in atomic number right there. That's down here, the lanthanide series. And so even though this is row 6, 6 minus 2, this is a 4f. And if we count over, there's 14 spots. So the next thing to fill would be 4f14. All right. Then after we finish the lanthanide series at ytterbium, again, atomic number from 70, we go to 71. And this now, even though it's row 6, this is our 5D for lutetium. 5D fills at 10. That would take us to mercury. And then to finish out and go to bismuth, we're back to what I call normal counting, row 6. So 6p1, 2, 3. So bismuth would be 6p3. So order of filling, right? I have 54 electrons in the xenon symbol because it's atomic number 54. 56, 70, 80, 83 electrons are here. So all the electrons are accounted for. That's good. Now, what are the valence electrons? Okay, valence electrons in this case, the D is full, the F is full. Those are not valence, those are core. So we just look at the highest occupied shell. So this would be the 6s2 and the 6p3. So if it's a representative element, meaning not a transition element, then the valence electrons are just, they follow the rule. They're the highest occupied shell. That makes sense. If it is a transition element, then it's the highest occupied shell and any unfilled D. So molybdenum had 6 total valence electrons, S1D5, whereas the bismuth has 5 valence electrons, the S2P3. All right, so I am going to take a quick break here. We don't have a ton. We could probably just go through and finish, but I want to do 5 minutes just in case anybody has questions or they want to get a glass of water or something. So my computer tells me it's 12:20. Let me come back at 12:25. Let me know if you have any questions, but otherwise I'll do a quick 5-minute break. Okay, so one thing I noticed during the break is the question for the last 2 examples we looked at said to give the complete and noble gas core abbreviated configuration. Personally, when you have large elements like bismuth, why would you do the complete configuration? Like the noble gas core abbreviated is so much simpler. So, I mean, we could have gone 1s2, 2s2, 2p6 and gone all the way through, but why would we? So I just forgot to cross that out. So just if you were wondering, I just forgot to cross it out. Okay, so everything we've looked at and talked about so far is always just the atom. We're not looking at electrons coming or going. And so what we're going to go into next is looking at the electron configuration of ions. So the big thing to remember here is what we learned in the beginning: metals always lose electrons. And when they lose those negative particles, they become positive ions, cations. And if it's a nonmetal, close to filling out the S2P6 structure and close to feeling like a noble gas, they are instead going to gain electrons. And if you gain negative particles, you become negative ions, and we call those anions. So that's drawing on from what we learned in the beginning. So if I just go back up here to bismuth, for example, right? So bismuth might confuse you at first because we learned, right, these are metals over on the left side. And when you get over here to bismuth, you might be like, well, wait, is that a nonmetal? But you want to remember, we've got that metalloid stair step. And I also have a pen that's running out of ink. So here's my metalloid stair step. All right, so bismuth is in fact a metal. And that means that it should lose electrons to form a positive cation. Bismuth is one of our type 2 cations. There are 2 or more possible charges. If we were going to name a compound with bismuth in it, we'd have to use that Roman numeral, like we learned in nomenclature. And if I told you now, you know what, bismuth has either a +3 or a +5 charge. Those are the 2 common charges for bismuth. Now I think it makes total sense, right? So rather than learning this in the beginning, which a lot of textbooks will do, they'll have you learn atomic structure first and then do the nomenclature, or like kind of do them right at the same time. Then that might help you memorize your charges, right? But to just not have any of this information and say, hey, just always remember bismuth is either +3 or +5, it'd be hard to make sense of that. So what happens is, right, you can see this, it either loses the 6p3 to become a +3 charge, or it loses all of the valence electrons to become a +5 charge. All right, so that's just on the side. But my point there I was trying to make is that metals always lose electrons, so they lose those valence electrons. All right, so we're going to look at electron configurations for these particular ions. All right, so selenium, -2, we looked at this earlier. All right, so selenium, we started out with the 34 electrons, and we talked about it having an argon core, and then past that it would have the 4s2, 3d10, 4p4. But if we're looking at the selenium anion with a -2 charge, which means it has 2 extra negative particles. So instead of 34, it has now 36 electrons total. Then this is now going to be what's called isoelectronic, which means iso, the same, electron structure, isoelectronic. Selenium, -2, right, picking up 2 electrons to now have 36, is going to match the configuration of krypton. So a lot of times this question confuses students because you're like, wait a minute, the noble gas core, I thought you just told me you go up a row into the end. That's true for the atom. In the case of the atom, we always do that. We go up all the way to the end, argon core for selenium. But now we're looking at the selenium ion. That's the difference. And so now we're going from 34 to 36 electrons. And now the noble gas abbreviation is krypton. And the representative elements, again, not the type 2 metals that we just talked about with bismuth, but the representative elements, that's typically what they want. The whole reason why they form ions and covalent bonding is because they want to look like a noble gas structure. So chlorine always picks up 1 because it wants to feel like argon. Fluorine always picks up 1 because it wants to feel like neon. Sulfur always likes to pick up 2 because it wants to look like argon, right? So if we're looking at S and P elements, right, not transition elements, because again, they're always weird. If they've gained electrons, we add that number of electrons right to the atomic number to get our total, and that should match a noble gas. Right now, I'm just going to throw in another one here that's not in the list. I'm just going to kind of look at this in a sort of opposite scenario. Let's say I've got strontium +2. All right, so if I look at my strontium atom, it has 38 electrons. But if it's +2, it's lost 2. So instead of 38, it now has 36 electrons. And so that means it also matches that electron configuration for krypton. So these 2 ions right here, right, those are isoelectronic. They have the same electron structure. The selenium ion, the strontium ion. You could also add to that the bromine ion, which is -1, looks like krypton. Right, those are isoelectronic. So the S and P elements, for the most part, again, not the type 2 cations like bismuth. There's always an asterisk with chemistry. But otherwise, the S and P elements, they want to end up looking and feeling like a noble gas structure. So when you do a noble gas core abbreviated structure for an ion of an S and P element, typically that's how it ends up, right? You're going to end up at a noble gas structure. Now, lead, not quite as lucky, right? So lead +2. When I look at lead here with 82 electrons, if it's lost 2, it now has 80, but that's not a noble gas. So I can't just say, hey, it looks like mercury. That means now I got to go through the whole motions, right? So I would have my xenon core. Then past that, we'd have our 6s2, our 4, and why did I put a P? I'm sorry. 4, let me just start over. Our 4f14. Then we'd have our 5d10. All right, and now normally what would finish this out for lead is you'd have your 6p2. But if it's a +2, that's what's been lost. So it's lost the 6p2. So for most, and I do say most, again, there's an asterisk coming. For most elements, you start with the complete configuration. And then when you look at what happens to the ion, whatever was the last to fill is the first to go, right? So like when we were filling the atomic structure for lead, we had a xenon core, 6s2, 4f14, 5d10, finished out the 6p2. But if it's lost 2, it loses that last thing that we filled. The transition elements, however, this is where writing it the way the book does might be advantageous, right? So if I have zinc +2, and I'm going to write this one out because I think it's confusing. When we do zinc, it has an argon core, and then it has 4s2 and 3d10, right? That's the complete configuration for the zinc atom, not the ion, right? So that's the whole thing. So what happens with your transition elements is you fill the 4s and then you fill the 3d. But then when you ionize, you take the 4s before the 3d. And that's actually true if the d is filled or not filled. Either way, it's the same. You take the 4s first. So what you're left with for the zinc ion is an argon core and then 3d10. So I'm just going to do another transition element here really quick, because I remember when I was first learning this, I was like, but wait, that doesn't make a ton of sense, right? So let's say we were looking at iron 3, all right? So ferric, all right? So if I start with just iron as the atom, it has an argon core and then 4s2 and 3d6. It's the 6th spot in the D block. So that's the atom. If I'm going to lose 3 electrons here, even though we fill the 4s before the 3d, we take away the 4s before the 3d, and that's only 2 electrons. We need to take another one away from the d. So what we're left with here, let me cross it out, is the argon with 3d5 left, all right? So I don't think that that'll come up too much, but it is something kind of interesting to think about, that the D transition elements, the S fills before the D, but when we take the electrons away, we take away the S before the D. That kind of seems counterintuitive, right? Because it seems like, hey, you just told me energetically 4s is better than 3d, so the electron prefers to sit there. But then when I go to take it away, I got to take away the 4s before the 3d. All right. And again, the way I kind of made sense of that was, if I'm thinking about removing an electron, I'm going to, of course, remove from the highest occupied shell first. So even though the 3d electrons aren't as stabilized as the 4s are still farther away from the nucleus than the 3d. So that was sort of how I rationalized it in my head. Now, magnetic properties, this is going to ask us to look at whether or not the electron, the orbital diagram, those are the arrows, are paired or unpaired. And I have to tell you, it's a simple mistake, but I made it when I was a student because I wasn't paying close enough attention. In my mind, I think para would mean paired, and it's not. You want to think di, meaning in twos, right? So di for two. So if you look at an orbital diagram with the boxes and the arrows, and all of the arrows are paired, so everything is in sets of two, it is diamagnetic. If you have electrons that have like a single in a box where they're unpaired, that is paramagnetic. And what this will allow us to kind of understand is that when you have unpaired electrons, they will show an attraction to a magnetic field. So anything like this iron 3 with 5 unpaired electrons, that would be paramagnetic. All right, so iron 3, unpaired electrons, paramagnetic. Whereas the zinc ion, right, the argon, those obviously are all paired. The 3d10 is all paired. So this is diamagnetic. All right, and again, just not paying close enough attention when I was a student and flying through this. I remember I had it backwards. I thought para would mean paired, and it's not. It's unpaired. So just remember di for two, right? So diamagnetic means everything is in twos when it comes to the orbital diagram. So let's look at nickel and figure out how many unpaired electrons there are, and then say if it's going to be paramagnetic or diamagnetic. So nickel, right? It's got an argon core, and we're looking at the atom, so we don't have to worry about any, losing electrons or anything like that here. So kind of back to standard, we have an argon core, we have 4s2, and then nickel is 3d8. Not one of the exceptions either that we have to worry about. If the subshell is full, we know that those are paired, so we don't have to worry about that. We just have to worry about the last thing that we wrote down. So remember, for D, we should have 5 boxes. All right, 5 different orbitals, and we have 8 electrons. So we're going to go up, 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 up for the first 5, and then back on the left, down 6, 7, 8. All right, so there's my 8 electrons. So what I can see here is I have 2 unpaired electrons, and so that would make nickel paramagnetic, because again, not everything is in twos. Right, so diamagnetic, di meaning 2. So if all of your electrons are in twos and everything is paired, then you know diamagnetic. But if you have unpaired electrons, then it's paramagnetic. All right, let's do a couple more on the next page. All right, let's look at the sulfide ion. So sulfur with a -2 charge. Sulfur with a -2 charge, that means that there would be 18 total electrons, because sulfur starts out with 16, that's the atomic number, and if it's picked up 2, it has 18 total electrons. This is going to match the configuration of argon, and if you have a noble gas configuration, there's no unpaired electrons, so this is diamagnetic. Everything would be in twos. All right, the iron atom, all right, iron with no charge, we saw this one earlier, argon core, 4s2, 3d6. So focusing on the D with 5 different orbitals, we would go up in each of those first 5 boxes, and then we pair down for that last 6th electron. So we have 4 unpaired electrons. Oh, that didn't come out very well. All right, sorry, 4 unpaired electrons. So again, this one would be paramagnetic. All right. And then the last one here is the cadmium ion. All right, cadmium is like zinc. It's always a +2 charge. It wasn't on the diagonal, so I don't make you remember that one, because I think the diagonal is just nice and easy. If I look at my periodic table, right, I wanted you to remember 3 for aluminum, +2 for zinc, +1 for silver. Cadmium is just like zinc. It's always a 2. It's a +2. So if I look at my noble gas core for cadmium, let me bring this back, sorry. Here's my cadmium. Noble gas core would be krypton. And then what we talked about was we've lost the 5s2 here. So what we have left is the 4d10. And if I know it's 4d10, right, then that's the most I can fit. All are going to be paired. So this is going to be diamagnetic. Forgot the A. I'm having a hard time writing today. Diamagnetic. All right, so di again, think everything is in twos. All right, so the question there, we just answered it. Which ones are diamagnetic? Which ones are paramagnetic? So again, it tripped me up when I was a student. Diamagnetic, everything is paired. paramagnetic, things are not paired. You have some electrons that are not paired. All right, then the last part of the section is looking at some trends. So refreshing maybe about this chapter, no stoichiometry, right? That's unusual. Very little math. I mean, we're just kind of counting electrons and that's it. And this is going to be no different. We're going to look at periodic trends. There were 3 that we learned in intro chem. We had atomic radius or size, ionization energy, and electronegativity. There's one more here for Chem 1. It's called metallic character, but that one, to me, that one's an easy one. So atomic radius, this is just general trends. Like, hey, if I go down a family, what happens to atomic radius? Or if I go across the periodic table, what happens to atomic radius? So just very general trends that we see. The atomic radius, the first thing is, if we go down a family on the periodic table, what happens to the size of the atom? And I think that everybody sees this very intuitively, right? If I'm going down the periodic table, let's say I'm looking at lithium, then sodium, then potassium, then rubidium, then cesium. We know that the atom is getting larger as we do that. We're adding on energy shells. So we think, okay, here's my nucleus, first shell, second shell, third shell, right? And the radius is the distance from the nucleus to the highest occupied shell. So it makes sense. Cesium is going to be a lot bigger than lithium, right? So your atomic radius increases as you go down a family. The side-to-side trend tripped me up because I remember thinking, all right, if I'm just looking at row 3, like from sodium, magnesium over here, aluminum, silicon, phosphorus, right? All in that row 3. What I linked it to was the number of electrons. And I thought, well, hey, the more electrons you have, the bigger it is, but that's not true. Because what happens here is if I imagine, and I'm just going to write this out here. Let's say I've got my sodium, 11 protons, 11 electrons. And then over on the right, I've got chlorine, 17 protons, 17 electrons. Both of those elements are in row 3. So if I think about my nucleus in the center, first shell, second shell, third shell, nucleus in the center, first shell, second shell, third shell. So let's pretend I can draw, and those are the exact same size. Then what you might think, okay, if I'm in the same row, then the size should be the same. If I go sodium, magnesium, aluminum, right? If I just go over row 3, all of those have their outermost electrons in the third shell. And if I think about that third shell being stuck in space, then all of them have the same radius. But what we learned when we talked about the energy transition in the last chapter, right? That energy of transition, we always put the little qualifier on it. This is for a hydrogen atom, And that's because what we talked about was those shells actually can fluctuate, they change in radius. They're not always stuck in space. So if I think about going across the periodic table to the right, even though both sodium and chlorine have electrons in the third shell, what's different is with chlorine, I have more and more positive getting in the center, in the nucleus, than I do with the sodium. Sodium only has 11 positive particles, but chlorine has 17. And what we know about positive particles and negative particles is they attract. So because we have a higher positive charge in the nucleus, it does a better job at bringing those outermost electrons in, not into a different shell, but just contracting the radius. So it turns out that the chlorine is smaller than the sodium. The sodium is slightly larger. And again, it's because it has the higher positive charge in the nucleus. So when you look at your atomic radius trend back in the notes, when you're looking at the side-to-side trend, atomic radius actually increases as you go to the left. So as long as we're in the same row, that's the thing. You have to only compare apples with apples. So you have to only compare elements in the same row. If we're in the same row, we know elements on the left are bigger than elements on the right. If we're in the same column, then elements at the bottom are bigger than elements at the top. So the way I remember this to make it sort of easy to me for the trends is I went to my periodic table and I looked, okay, what element would that be? Well, if I go all the way to the end and down, francium, right? So if I'm looking at my periodic table, we expect francium to have the highest radius. So the way I remembered it was, because I thought this made it easy, AR points to FR, right? So if I can remember that, then I can remember the trend is go to the left and down. That's how your atomic radius increases. All right. So we're gonna look at examples here in just a second, but let me talk about ionic radius first. Ionic radius is only comparing an atom and its corresponding ion. So in other words, you have to compare the sodium atom with the sodium ion. You can't do the comparison of the sodium atom and the chlorine ion. Like that's not what we're doing. We're just looking at the atom and its ion, the corresponding ion. So this one does make sense to me, that when you lose electrons, right, the cation is always going to be smaller than the original atom. But if you lose electrons, it's going to shrink, become smaller. And the reason for that makes sense. Like if I look at sodium, right, going back to my picture, sodium, the atom, had 3 occupied shells. And in that third shell, there's an S1 electron. Well, if I become +1, it empties that shell entirely. And now it only has 2 occupied shells. So the sodium ion only has 2 shells, whereas the sodium atom has 3 shells. So it always made sense to me that the cation is always going to be smaller than the atom. The opposite is true for the anion. As you gain electrons, it's going to become bigger, because that what's called the effective nuclear charge, the positive charge in the center, is not as effective because now I've got more negative particles. So the atom is always smaller than the anion. So I think the easy way to remember that is if you lose electrons, you're going to get smaller. If you gain electrons, you're going to get bigger. That kind of makes it nice and simple. So if I have this type of questions on the test or on the practice quizzes, I give you some elements and I say, okay, put them in order of increasing atomic radius. Really what I'm asking you is to remember the trend. So if I go to my periodic table, I've got beryllium, fluorine, and nitrogen. So I go to my periodic table, here's beryllium, here's nitrogen, here's fluorine, right? So they're all in the same row. So I know fluorine should be the smallest, right? So fluorine is going to be the smallest, right? Then we're going to have nitrogen, and then beryllium should be the largest or the biggest, right? Because we know it increases as we go across to the left. If I look at barium, beryllium, and calcium, these are in the same column. So beryllium, calcium, and barium. So beryllium should be the smallest, only 2 shells. Calcium 4 shells, barium the largest with 6. So we expect beryllium to be the smallest, then calcium, and then barium at the end. All right, then the last one here, we've got chlorine, fluorine, and sulfur. So they're right here next to each other, right? So the smallest for sure we know is fluorine because it only has 2 shells. Then what we look at is the relationship between chlorine and sulfur. And what we know is as we go closer to francium, so as we go to the left and down, we get larger. So fluorine should be the smallest, then chlorine, and then sulfur should be the biggest. So fluorine the smallest, chlorine in the middle, sulfur is the largest, right? So that's how we do the trends for atomic radius. So that was the first of 4. All right, so atomic radius increased to the left and down. AR points to FR. Ionization energy, the next one, is the energy required to remove an electron. All right, so we're gonna make these turn into cations. We're gonna take an electron away. All right, and they're measured, they're tabulated. You can have them as IE1, IE2, IE3, meaning the energy to take away the first electron, energy to take away the second electron, etc. Now, what we know looking at the periodic table is that metals lose their electrons pretty readily, right? We know that. In fact, some are so reactive that we don't even find them in nature as elements, like sodium. It's always as an ion, which means it must give up its electron pretty easily. And then we know as we're on the right side of the periodic table, nonmetals don't want to lose electrons, they like to gain. So what we can predict is that the energy required to remove an electron is going to get way worse as we go across the table to the right. And that is true, right? Ionization energy increases as we go to the right. As that valence shell starts to get closer and closer to being full, the less likely it will be to want to remove an electron. Now, the family trend kind of goes with the atomic radius. And that one, I think, do you think it's easier to remove an electron that's right next to the nucleus or an electron that's maybe 3 shells out, right? If I want to move this, remove that electron or this electron, which one would be worse? It's way harder to remove an electron closer to the nucleus, right? Because that it's so happy there. Whereas if it's an electron away from the nucleus, much farther out, it's going to be so much easier to take it away. That electrostatic force isn't as strong because the electron is so much further away from the nucleus. So ionization energy, the energy required to remove an electron, gets much higher as we go up a family, and the size of the atom gets smaller and smaller and smaller. So if I look at my periodic table and I go up and to the right, helium. So we expect helium to have the highest ionization energy. And in fact, it does, right? Because not only is it a 1s2 configuration, so the electron is in that first shell, but it's also a noble gas. It's highly stable. It is possible to take an electron from helium, but it makes it very unhappy, right? So what I remembered here is IE for ionization energy points to HE, right? So helium is our element with the highest ionization energy. So what I can see here, comparing the two trends, let me zoom out here for a second, is the two trends we talked about are exact opposites, right? So ionization energy increases up and to the right, atomic radius increases to the left and down. So they are exact opposites. That kind of makes it easy. All right, so if we look at the same, almost the same set of elements that we had on the last example, but now we look at ionization energy instead, so on the next page. All right, let's look at beryllium, fluorine, and nitrogen and put them in order of increasing ionization energy. All right, so beryllium, and then nitrogen and fluorine. Fluorine is the closest to feeling like a noble gas. It's going to be the hardest to take away an electron there. So beryllium should have the weakest ionization energy, then nitrogen, and then fluorine. So if you compare that to what we did for that same set of three elements for atomic radius, it is the exact opposite. And right, that's what we said, the trend is the exact opposite. If I look at barium, beryllium, and calcium, they're in the same family. All right, so beryllium, calcium, barium. We're going to remove an outermost valence electron from each of those. Probably the easiest from barium because it's 6 shells out. Barium tougher because it's in the second shell. So we expect barium to have the lowest ionization energy, then the calcium, and then the beryllium, because the beryllium is the smallest in size. All right, again, the exact opposite of what we got when we were looking at atomic radius. All right, last one here. If I gave you this set here, fluorine, phosphorus, and sulfur. Let me get a different pen because they're starting to get messy. So fluorine, phosphorus, and sulfur, right? Ionization energy, IE points to HE. So the one that it should be hardest to take away is the one closest to helium. So fluorine should be the worst. Phosphorus should be easier, right? So in terms of ionization energy, phosphorus should be the easiest to take away electron, then sulfur, then fluorine. All right. Electron affinity, also called electronegativity. This one's going to need a big star because we're going to need this when we do our Lewis structures. You'll see that. All right. Electron affinity and electronegativity, it's basically the same thing. It's just a different measurement. But electronegativity it's a scale, 0 to 4. Our most electronegative element has a value of 4. Electron affinity is actually an energy with gaining an electron. So that associated energy. But they're basically measuring the same thing. How bad does the atom want to gain an electron? So what we can already assume is that noble gases don't want to have any part of this, right? Noble gases like neon have what every other element is looking for. They're incredibly stable. They do not want to form, they don't want to gain an electron. So we are going to take out noble gases altogether. So just pretend that column doesn't exist on the periodic table, just for this trend. So what we know is as we go across the periodic table to the right, that desire to gain electrons obviously gets bigger and bigger and bigger, right? Fluorine is going to always gain an electron. Lithium is always going to lose. So as we go across the periodic table to the right, electron affinity or electronegativity increases. The family trend within a column, the smaller the atom is, the better seat it can offer the electron, right? Hey, I can give you a 1s space rather than a 5s space or whatever it is. So as you go up the periodic table and you look at elements that are smaller in size, they can offer a more attractive seat to the electron. So your trend for electronegativity, it looks exactly like the trend that we had for ionization energy. And that made sense to me, right? The more the atom wants to gain an electron, the more difficult it should be to gain or to take one away, right? That kind of made sense to me. So the trend looks the same. The only difference is we have to take away the noble gas family. So if I look at my trend, right, we said talk about going up and to the right. But now if I take away my noble gas family, fluorine is our most electronegative element. All right, so fluorine is our most electronegative element. And if you remember, we'll talk about this when we do Lewis structures. But if you remember your polyatomic ions like chlorate, bromate, iodate, if you ever were like, well, why isn't there fluorate, right? Why isn't there FO3 -1? When there's ClO3 and BrO3 and IO3, why not fluorate? The reason is when we do Lewis structures, we're going to see that the halogen is the center element. And fluorine, because it is the only element more electronegative than oxygen, it doesn't form oxyanions with oxygen. So there's no fluorate or fluorite. There is actually fluorite to a mineral geologist because that's something, it's called calcium fluoride to a chemist, but it's called fluorite to a geologist. But that's an aside, not to be confusing. The polyatomic ion fluorite does not exist, right? So that's why, because fluorine is our most electronegative element. Now, the one that's new that we didn't do an intro is called metallic character. And this is another one that I thought made total sense because when you look at the periodic table, the first trend, left and right, we know metals are on the left, non-metals are on the right, right? We know that. So we know metallic character on the periodic table increases as we go to the left. So that was the first one that was easy. Then the family trend, easy thing to think about here, is let's say we look at the carbon family, right? Carbon, non-metal, silicon, germanium, metalloid, tin and lead, metal. So we can see this. Metallic character increases as we go down a family. So increases as we go down a family. So if I look at that one, that looks a lot like atomic radius, the very first trend that we did. So metallic character, we expect francium to be the largest. So what we have here are two trends that look exactly the same, and then two trends that kind of look exactly the same with just the exception of the noble gases. So just to summarize, all right, metallic character and atomic radius or atomic size, I see both. I like atomic radius because I like the AR goes to FR. The trend is increase to the left and down. Francium should be the most. Highest metallic character, largest in size. All right, ionization energy. Remember, IE goes to HE, increasing up and to the right, exact opposite trend, right? And then electronegativity looks the same, up and to the right, we just stop a column short, we go to fluorine. All right, so those are our four trends, and that completes chapter 9. So a lot of conceptual information. A lot of students really like this chapter because it's not, there's no stoichiometry, there's no gas laws. It's a little bit easier. The electron configurations, orbital diagrams, just good things to practice. Make sure that you got it. And then what we'll now segue into is start looking at Lewis structures and bonding. How do we get that noble gas feeling for the elements in covalent bonds and ionic bonds? And then we'll talk about, okay, now that we know that, how do intermolecular forces work? What are the forces that hold the molecules together? All right, so we're done a little early, which is nice little change, but that's it for me today for the chapter. If you have any questions, let me know, but otherwise I'll see you back Thursday for chapter 10.